pleasure to have Dr. Kwo with us. So Dr. Kwo received his PhD degree in atmospheric science from Colorado State University, specialized in reductive transfer. He is now affiliated with NASA Goddard, and he's also the chief data scientist of his company based in LLC. Dr. Kwo considers himself a disruptive thinker, commonly known as boat rocker or troublemaker, because he likes to question the existing ways of doing things. So his disruptiveness hasn't mellowed with advancement of age, which he himself is curious about and questioning why. He has been working with volumes and diverse geodata since he was exposed to Landsat and AVA data, considered big at the time too. And he learned and applied then various data processing techniques, which are now considered as machine learning and artificial intelligence. And he will be doing a demo right before his talk. So let's welcome the speaker.
Thank you. Thank you. Thank you. Many of you, some of you know me, and I go by my last name, Kwo. So that's why Kwo is underlined there. All right. So today my presentation is getting fusion ready. That will become clearer as the presentation goes on. And for data-intensive geospatial temporal analysis, that's quite a mouthful, but basically big Earth data, if you just shorten it. All right, so this is the outline. I will introduce the for this presentation, and also a big part of my data information technology research is the 80-20 dilemma. Then I will conduct the demo, and then after demo will be the slide presentation. These are interrelated. So first is the 80-20 dilemma, and this is on the flyer, so you have probably seen this. Okay, most data scientists spend only 20% of their time on actual data analysis, and 80% of their time in doing what I call, collectively, data preparation, which is an inefficient data strategy, to say the obvious. Okay, so I'm going to demonstrate, what kind of a data preparation and how a data preparation can help us scale not only volume, but also variety. Okay, volume, we know how to scale. We apply parallel processing. But the thing is that if we cannot scale variety at the same time, simultaneously, then the data volume scaling will be partial, ineffective, okay? This is especially the case for earth science analysis, which we do integrative analysis of diverse data sets. Like say the demo has been contributed by my Access STAIR team. Okay, so these are the team members of the STAIR team, and their Mike Riley is actually the PI of this project. So the synopsis of this demonstration is that each inspector, we have what I call the jelly beans, and GEOLLY, jelly beans, okay? And then each instructor is responsible for the quality evaluation, such as weight, sugar content, shape or color consistency, flavor consistency, okay, of the jelly beans. For obviously, if you want to evaluate color consistency, you better do it by color. And using this hypothetical scenario, we want to demonstrate data placement alignment, and you will see, it will become clear what that means. Data placement and alignment, or it is also known as data collocation in various compute storage architectures for data-intensive analysis. Okay. Okay, data placement alignment is very important, and that's the key for being able to scale, to data-intensive big data, efficiently scale to the big data. Okay, so introduction. I originally planned to buy actual jelly beans, but I call them GEO-LLY beans, but the jelly beans have too many flavors. So I decided to settle on Skittles, but I still call them jelly beans. Only 5 flavors with in 5 corresponding colors. So obviously for them to do the analysis, meaning the quality evaluation, it's best they separate out the color first, right? Okay, so now this symbolizes a narrow mouth jar with all the jelly beans. This symbolizes our internet. So if they need to get the data from here, then each one can get, only a small portion at a time, and they have to time share, right? Okay, but the Act 0 is serial processing, and that's going to be really, really slow, right? So we are not going to demonstrate that, otherwise we'll be here the whole afternoon. So this is kind of like our internet. It has very large storage, but very slow bandwidth. So I can put this in this white open bin, and this white open bin symbolizes our parallel data file system, right? So you have parallel data file system. Each of them can get, few of them can get a scoop at the same time, and you will be able to get the data out that you want to analyze in a more efficient and a high-performing way. But better yet is that we could put these on local storage. So you can put on the gloves first, and Mike, please open the bins for them, the container. Whoa, I closed it tight. Yeah, we are the operating system. Okay, all right. Now, I can ask then each, inspector separate out the color, a small batch each. Okay, please commence doing it. And this is a competition. This is a competition. Hey, I actually weighed these, so they all have the same mass. Okay, they all have the same mass. So there's no one. Okay, you can see this is kind of a slow process, even like this, right? So what if we add some, random access memory or cache? Okay, so now if you put some in here and then start sorting, it becomes easier, right? It becomes faster. Okay, so while we are sorting, I need to give them each one a designated color, right? So he will have white, yellow. So after they sorted, they have, each instructor is responsible for one color. He will be responsible for Y. He will be responsible for green, G. And he will be responsible for R, red. And he for orange, O. Man, look what that spelled. luckily we have a P for purple. All right, see, now with the random access memory, or if you want to call it cache, it becomes much more, much better, right? The performance is better. Unless you knocked off a glass or something. You lost some? Or you ate some? No. Okay, all right. Okay, don't eat them yet. Oh, someone lost some. Don't put that back in. So we want to, oh, here's another one. Here's another one. Okay, so now, see, after they are done, now they're about ready, right? Almost ready for their analysis. But now they have to pass the same color, the yellow to him, and green to him, and red to him, and orange to him, obviously purple to him, right? So you have to pass them around. So this is data communication, all right? So we want to commence the analysis. If the data, they are not already at the location, data communication commences. So this is, if you are on a high performance computing facility, you have a fast interconnect, this will be fast, but if you are not so lucky, this can take up most of your time, your processing time. All right, so this is the demonstration for what I call local storage system with dedicated bandwidth. So when they are doing this, sorting them, it's local file system. They are doing it locally, right? And then it's dedicated because they don't need to pass. So that even worse, and even the more dumb way is to pass each beans to the right person, right? So, and at least that we picked a kind of smart way of doing this. So that will cause even more trouble. It was even slower. But another better way is co-located already, right? So what if I have the storage already aligned according to my processing requirement. See, at this point, they haven't started a real analysis yet. This part is just what? Data preparation. So we waste a lot of the, sorry about that. So we waste a lot of the processing actually in the data preparation. So the moral of the story, color in this case is the primary key for jelly beans quality evaluation analysis, right? If the jelly beans are pre-sorted, they can be, partitioned to the individuals, then we save a lot of time. And then similarly, the primary key for all the geospatial temporal data is their geospatial temporal coordinates. Okay, remember that. It's analogous to the color of all the jelly beans. And also, most of earth science in integrative analysis require what I call spatial temporal coincidences. In other words, we always, for the most part, always want to have different data set, right? At the same place, the same time. We want to analyze at the same place, same time. Say, for example, if I do analysis for simulation or input, or we evaluate simulation data, simulation output result, we always analyze them for the same place, same time. okay? So now, if we can align the data on the local storage or whether it's a hard drive, or memory, then the processing becomes a whole lot more scalable. Okay, now here comes the problem, right? That's what my next slide presentation will be about. And there's a complication though. We are not only interested in just the location, the geospatial location alone, because all of the data have some other spatiotemporal connotations, meaning the resolution. So we are actually interested in a neighborhood, and this neighborhood size is varying from data set to data set. This neighborhood from instrument to instrument, from model to model, this model output to model output, this resolution can vary. So an effective index, or what we call the primary key, right? In geospatial temporal, for the geospatial temporal data analysis, need to take both into account, not just the location alone. Okay, so now we get into my slide presentation. It's called the STARE for fusion ready data intensive geospatial temporal analysis. Okay, and many people know about this, especially those affiliated with NASA NOAA and have been using their product. Oh, thank you so much. You guys can go back and enjoy your pizza. I'm sorry, I forgot about you. And volunteers. Thank you. Thank you. So in the Earth observing system, data information system, we have 3 kinds of data models: gridded data, SWOT data, and point data, right? And right now, they're all organized using the array data structure. But the problem is that, you see, for grid, you may use L for longitude, M for latitude, but swath, you use I for cross track and use J for, the R and J, these doesn't matter. J for a long track, and a point, you just organize them in a table, or 1D vector, right? So the problem, the variety challenge in geospatial temporal data is basically this. We know that we use array data structure, and the array dimensions usually correspond to the physical dimensions, right? So we have a ij for space, and maybe some other for t, and so on. But this correspondence, or what we call a mapping from the index space to the physical space, right? Between an array and the physical references is changing from data set to data set, from data granule to data granule. So think of the modus data, right? The ij for each granule means something different, a different location. The same ij means a different location. So this is what I call the data packaging peculiarity. I put red on it, so because I'm going to talk about that later. About data packaging, or what is a better way for data packaging. Analysis, we concern ultimately with the physical reference. We seldom in our report, refer to the INJs of this array, right? We always refer to, the geolocation, the latitude, longitude, and whatnot of the analysis that we are doing. So, but analyses are presently forced to go from the array reference, or indices, through the ever-changing mapping to a physical reference. This is what leads to our lack of scalability in the gist, the variety challenge that's facing us in geospatial temporal analysis. The analysis will become more scalable if a constant correspondence between array and the physical references can be established, right? So STAIR established such a uniform correspondence for geospatial temporal data. Okay, so meeting the challenge with the STAIR. Well, what does the STAIR stand for? STAIR stands for Spatial Temporal Adaptive Resolution Encoding. As I mentioned to you before, it's not just the location reference, but we also need the neighborhood. In other words, the location, the resolution. Okay, STAIR has two components. The spatial component, we use a hierarchical triangular mesh, HTM, that encodes the neighborhood on a sphere hierarchically based on spherical triangles. You will see in a minute exactly what that means. And we have temporal elements, and then we use hierarchical cylindrical partition, right? And it encodes the neighborhood on the timeline hierarchically based on cylindrical unit. Okay, this is the hierarchical triangular mesh. This is nothing new, around for more than 20 years. Okay, the Sky Survey, Sloan Digital Sky Survey, people uses this encoding, but it uses it slightly differently from how we use it. Okay, you start with an octahedron. Octahedron has 8 sides. It's a platonic solid. It really doesn't matter which platonic solid you pick. You can follow the same procedure. But we picked the 8-sided octahedron because 8 is 2 to the power of 3. So using 3 bits, I can number the facets of this octahedron. Okay, the step of the mesh, establishing the mesh is, okay, you start with the inscribing octahedron, you bisect the edge, and you project the edge from the center of the sphere to the surface of the sphere. This way, you have now 4 spherical triangles. Okay, you keep doing it until you say, I'm okay now, because we are going to use the centroid of the tiny mesh triangle to denote the geolocation. So you go down to a point, but you quadruplicate. I call this process quadrification. You quadruplicate to a certain depth, then your the size of your mesh triangle, your leaf triangles is matching your geolocation uncertainty requirement. Then you stop. Okay, so basically now from the top level, the 0th level down, they're all quadries. Okay, and then their numbering in the same level is always consecutive. Okay, so I need 3 bits for the first level, for the 0th level, then I need 2 bits, additional 2 bits every quadrification, right? So this is the resolution, kind of a table. So at the 11th resolution, diameter of that it covers the mesh triangle is already about 4 kilometers, and that's the GPM trim sort of resolution. And here you have the MODIS resolution, about 1 kilometer to about 250 meter. Okay, and then this we use only 23 levels, and then we already reach about 1 meter resolution. Okay, so the characteristic of, sorry about this. So Earth surface is indexed with just one 64-bit integer, okay? And that forms 8 quadries. All right, the precision reaches better than 10 cm, centimeter, when we at the 27th quadrification level. So then we will show you later that, we don't have that, do we? But anyway, we did an evaluation. The 2 floating point that long as we do it now, the best is they can do it is about 10 cm precipitation, and it varies from places to places too, from the latitude points. Okay, so now on a multinodal cluster, when a branch for a multinodal cluster, if we decided to remember that tree, if I decide to cut at the branch of that tree, then each branch I throw it to, I round robin or whatever, throw it to a cluster. Now, I do this for all the geospatial temporal data sets, they will be collocated, right? And now I need to, even hard for me to read. So let's go to an example. So for the 27 by qualification, it takes 54 bits, and then we need three bits for the original root octahedron. And we are not using the sign, the bit for sign, right? Because there is no negative spatial index. So now this uses 58 bits, 1 plus 3 plus 54. Then I still have, in a 64-bit integer, I still have 6 bit left. I use that 6 bit. 6 bit is, value ranges from 0 to 63. So just enough for me to point to the position, certain position of that 64-bit integer. So I use it to point to the qualification level that is most compatible but covering the data elements. All right, so now in one 64-bit array, I have geolocation and its neighborhood for a data point. I have the geolocation of the data point and also encodes the neighborhood of the data points. And this is a neighborhood, so we, like I said, if you chunk it if you decide to cut it at a certain level, what level do we cut here? 4th, right? Yes. Okay, the 4th level we cut, and we distribute, not distribute, we color the 4th level mesh triangles in this color. 16 shades of gray. Okay. So now, if I have a 16-node cluster, and I will, for the same shade, I put those data on the same cluster node. Okay, now if I do this for all the data, then they will be spatiotemporally aligned. And then when we are doing our integrative analysis, there is little, we reduced unnecessary, we minimized, reduced unnecessary data movements. This is how we will be able to scale in a variety, volume and variety. Okay, so people are worried about, all right, we're not used to your stair encoding. Have to. The thing is that we think, the lat long, we are more familiar with the lat long is only because that lat long in the data files, right? They are encoded too. They are encoded with floating point encoding. So how do you get the lat long? You go through the some interface, programming interface. For your right statement, you specify some format, and the right statement, that function, actually interpret that encoding for you and output something that is humanly readable, right? So you don't have to worry about the encoding, how it is encoded. You only need to use, if you want something human readable, you go through our stair API to read off the humanly readable latitude, longitude values. Okay, now we just talked about the spatial part. The temporal part is similar. We call it a hierarchical calendrical partition, and it's a hierarchical in a calendrical unit. You will see in a minute. We also use the least significant bits to denote the temporal resolution. It's fairly straightforward in conversion. Okay, so this is just an example. The final design and the implementation is a little different from this, but it captures the basic concept. So we use a certain range of bits to denote different things. So from we use 6 bits to resolution. We use 10 bits for milliseconds, 6 bits for second, and so on and so forth, right? And the type, meaning that we could have several different scales of the time scale. So the property of this stair, and the advantage of the stair is that it establishes direct and uniform connection between indices and the geospatial temporal references, including resolution, right? So when you have the resolution, say for example, you have one coarse resolution data, the resolution pointer is going to point at a higher level, sorry, a shallower level, right? And you have some other coarser resolution data, maybe a coarser resolution data. Resolution bit is pointed to some deeper level. Now you need to only compare the top one between the two. You know if this one contains this one. So it becomes a bitmap operation in finding coincidences. Right? So this is what makes it extremely fast and high performance. And I've shown Xinzong here a prototype that we built based upon this technology. And I can say that he is fairly impressed. What we can do, I also showed that to Ryan back there, and he was also very excited about what we could do. So you don't have to worry too much about this, but stair indices are sparse. So because of this thing, they are not consecutive. We use the data structures like the traditional computer science data structure, because those data structures can facilitate fast operations or computations on our computers. So increments, like array, jumping, strides, increment, those are fast, right? But stair is not like that. Stair, if you think about it, it's more like a key value. So you have the stair indices as key, and then you have your data as values for that key, spatiotemporal location. And it's more like a dictionary, like in Python dictionary. It's different from the conventional array data structure. And the stair indices can serve as the primary key in both database and key value technologies. For key value technology like MapReduce, those are key value technology for big data processing. So the most important thing is that stair enables spatiotemporal data alignment of diverse data sets, and then that's minimizing the data movement. What does that mean? What does data alignment mean? So this is an example. You see this, earlier. So I said that for the same shade, I will be putting them on the same node. Now this is a cartoon. So I have a node, and I have a data set, space and time, and a global data set. I cannot, really draw triangle volumes very effectively, so I use a square, but use your imagination. So I can chunk this into A parts, and I can put each part on a separate node, right? And then if I'm analyzing the whole globe, right, all the entire time in the whole globe, and everyone will do its part. So this is when we can scale volume. And then when we do for different diverse data sets, then it's better that this time and space are co-located. So they go on the same node where they can do comparisons at the node without shifting the data around. Okay, but there is a drawback with this naive partitioning of data. It's that North America is there. What if I just want to analyze that part? So now only one node will be analyzing, the other one will be sitting idle. So that we have a load imbalance. So to address that problem, then is of course to chunk the data into smaller chunks and distribute the smaller chunks. Then you have less opportunity or probability of running into the node imbalance situation. So now this is the more interesting part of. Remember that I mentioned before, there's a data packaging peculiarity. So the reason this is so hard to use is because we partition the data. We package the data according to the, a long track or cross track or a long track. We package it that way. Okay. Then once you package it that way, it's like a straight jacket. You put it on, and it's difficult to find the matching things from other data sets, right? So imagine if I use the stair hierarchy to package the data. We can choose a level, right, to start. Choose a shallower level to start. And then in each of the 4 parts, there will be another level. Each of the 4 parts packaged into what I call the virtual collection. Note that the HDF has the virtual data set capability that we can leverage. So now, actually, at this part, at some lower, deeper level, you actually have the actual data. But you can access this data all the way up the chain using the virtual data set. So now, if we package the data this way and disseminate them to put them onto even cloud, all right? Now, a big organization comes along, for example, NOAA, they want to process their data. They could use the upper level because they could afford they have more resources. They could afford fatter nodes with better, larger memory, faster computation. But if an individual scientist comes along and he doesn't have that much resources, and also he probably not interested in global data for a long period, right? Then he could use the smaller one. These are basically different levels of chunking in the parallel processing speak, parallel computation speak. So that's the end of my talk. The conclusion is that STAIR is a variety harmonizing technology for geospatial temporal data, enabling variety scaling in addition to volume scaling. All right, STAIR is adaptive to different compute storage architectures. So you could have a cluster with the nodes of that cluster with the local storage, and that's the most efficient way, by the way. Or you could have, in a high-end computing facility, you have only storage-less compute nodes, and you have to read off from the parallel file system. That is adaptive to both, as I mentioned earlier. And so the gist is that STAIR enables massive reduction in data preparation effort while making the analysis computation more efficient. All right. So STAIR, in my opinion, is poised to flip the 80-20 dilemma. The end. Thank you.
Questions?
So I do understand this is a very efficient indexing. I think this is the direction we should go. Can you elaborate what is the possibility for these stereo index the operation? How these stereo
There.
index can be operated?
Right.
You know, how,
Yes.
for example, just take, say, we have all different kind of variety of data,
Yes.
and now and a different resolution, and now we want to find one point or
Yeah.
do area average interpolation of that.
Right.
How we manipulate the index.
Okay, so the manipulation you will use the STAIR API or STAIR library that Mike is working on for the Access project. We just had our annual review, and the STAIR library is ready for interested developer user testing. Okay, so for that project, we proposed to give or to construct a STAIR companion to all the NASA data granules. Because NASA data granules, they already have latitude, longitude. And if we want to go in and change those, I mean, that's going to take a long time. So we say that we will have a lookup table, basically a lookup table that you have the array indices and then corresponding, STAIR indices for that granule. It is established to construct them as HDF formats, in the same format as the original source data. So that's our first step. Okay. Then we are working in that project also. We are working with the OpenDAP, because OpenDAP already have servers on many of the NASA centers that grab the data, do some lightweight analysis, so people to facilitate data exploration, really, not yet data analysis, not heavy lifting data analysis. For heavy lifting data analysis, right now, it's still grab it from FTP or whatnot, right? HTTP, download them, right? So that is the case. All right, then we have a plan. That's going to be our proposal as well, is to exactly doing what we just said in the last slide of constructing these hierarchical files using VDS. But the problem there, the real problem there is that how do we make it backward compatible so that people, when they are, because people have invested a lot in reading the current way, right? So we certainly don't want to have an abrupt change for them to, adapt it to our stairway. Right? So now it's best to have the backward compatibility, so they can read it the same way, but in the back end, the data are actually stored in the STAIR hierarchy, according to the STAIR hierarchy. So those are the things that we are doing right now.
Yeah, it sort of gets to my question. Have you actually tested this with some test examples where you've
Yes.
done the analysis, a classic problem of some large
Yes.
data set and done it both ways to see the performance?
Yes, actually, we did it for NASA Center of Computational Simulation, right? Climate simulation, NCCS. We did it for NCCS. Actually, we didn't compare it to the traditional, individual scientist way of using Python and processing the data. We use Dask, Python and Dask, and we beat them hands down. You may. We have a report. If you're interested, send me an email. I will give you that report. And the thing is that, okay, Many of you know that Pangeo is getting a lot of attention, right? Ask them to do integrative analysis. Ask them to do diverse data set integrative analysis. Okay, a lot of the problem, including Spark, okay, MapReduce, Hadoop, Spark, right? The problem is that they can only do pleasingly parallel problem. They want to scale up, they have to consider this too, because this is a big part, taking a big chunk out of their performance. The data preparation, being able to align. Come on, if you want to analyze two data sets for the same space and same time, if one data set is in node, whether it's in memory or storage, doesn't matter, and then the other one is in node J, the first thing you need to do is bring them together. This is what we call in database technologies called a join problem, right? You have to join them first. Otherwise, how can you do it? Or, another thing is that, okay, like I know that some of the planned strategy is that we regrid both to the same grid before I bring them together. But come on, it's the same problem. You still have to bring them together, right? So that's the problem. And then we do have, actually, that's our previous, we were preparing for this because I actually thought of this, started doing this, the design in 2014 or 15 timeframe. But it's very hard to make people understand the significance, the importance of this thing. So the acceptance is slow. Okay? But then, at that time, we also had, we were preparing for this because at that time we also had a NASA project doing regridding, working with, because we realized that a lot of the newer grid systems, they want to address the problem of the singularities at the pole, right? So you have a very fine resolution there, but not very fine at the equator if you use that long. And then you're wasting a lot of your computation time because of that fine resolution. So they want to have a more even, somewhat more quasi-equatorial grid. So when you go to that grid, a lot of people are not going to be familiar with them. It'll be just like, when they see a stair, wow, that's not something that I'm comfortable with, and I'm more used to latitude, longitude, and so on. So we anticipated all these things, and we had a project that's what you're actually doing the interface for regrading of different data and bring them together. So that is in our pocket, and when we have a good opportunity, they can marry together. Because this is only the first step. That's what I have been emphasizing. You bring the data together, that's only the first step. You haven't started the analysis yet. So if you want to compare, say, for example, ground observation of precipitation with the satellite measurements, you bring them together is only the first step. Then you have to do analysis, right? You have to do whatever, regrading and whatever, before you can commence the analysis. So that's our plan, basically from this point on.
So we have an online question.
Sure.
This is, could you elaborate why you use the triangle? How about octagon or another shape or a beehive shape? A beehive.
Oh, yes, but the beehive shapes, you could start with, say, for example, corrected me. I always forget that platonic solid. No, the one before, the 12-face one. The decadal. Huh? The 12-faced one, the 12 pentagon one. Decadal, the hedron. Keep forgetting the name of that. There's a 12-faced one with 5 pentagons. And that's if you start, partition those, you can get something like what we are really familiar with, soccer ball. But you always end up with 5 pentagons. And also, these pentagons and hexagons are made out of triangles anyway, right? So actually, it doesn't really matter a whole lot. As long as you can establish a hierarchy, effectively, they will work the same, right? So we could even start with cubes, and then you bisect them into spherical quadrilaterals, right? You could do that too. The thing is that you start with if you start with a platonic solid with more facets, then it's more equiareal. Still not exactly equiareal. Okay, still not equiareal, but it will be more equiareal. And you start with a smaller number of facets, then it will be less equiareal. In other words, at a certain at a given qualification level, the area variation of the mesh elements will be larger. So it really doesn't matter. And also, another thing is that 8 is exactly a power of 2. So that's why we picked it. But we are thinking of extending the library for other platonic solid as well.
Well, one key point to apply your method is to transfer or exchange between latitude, longitude, and this index. Right?
Yes.
So this exchange, how fast it can be, and will it be
conversion between the indices and the let alongs? How fast is it?
And the complexity of this transfer will be increased when the resolution might be higher.
I think we need to do a benchmark on those. But we have to have something to compare against.
Yeah, one thing I'm afraid of that when the resolution is very high, the transfer can be very costly.
Right now, the project we have, we are converting modus granules. How fast can that be done with on open dev system for one granule? I remember Gallagher gave us a number. I forgot what it was. He said it's several seconds.
Something of that nature.
Yeah. So one modus granule, that's a 1 kilometer resolution. Modus granule takes 10 seconds maybe, in that order. We have to get that number exactly, but talk to me. You know me, so send me an email, I will get it back to you.
Thank you.
So, okay, so with that, let's ramp up and thanks the speaker again.
Thank you.